Hi and welcome to Quick Add Maths on trigonometric graphs. I will start talking about this slide by referencing the diagram on the right. Here we have a point that is at the distance r from 0, 0 and it is moving in the direction of theta to complete a circle. The height component of r is its y value. So, as when theta moves from 0 to 90 degrees, its y component will move from 0 to r. As it moves towards 180 degrees, its y component becomes 0. And as it continues to 270 degrees, its y component becomes negative r, and so on. Now, when r is 1, sine theta is equal to y. And if you were to plot a graph of y versus theta, which is really sine theta versus theta, it will take the graphical form as shown below, where sine theta is a periodic function that repeats in shape every 360 degrees. Separately, if you take its horizontal component, which is labeled here as x, as theta moves from 0 to 90 degrees, x will move from being r to 0. As it moves from 90 to 180 degrees, x will change from 0 to minus r, and so on. Again, when r is 1, cos theta is equal to x. And in plotting the x versus theta graph, which in essence is also the cos theta versus theta graph, it is as shown as below, whereby cos theta is also a periodic function that repeats in its shape every 360 degrees. To plot the tangent theta versus theta graph, this would be like plotting a sine theta over cos theta versus theta graph. So again, when r is 1, sine theta is y, cos theta is x, and tangent theta would be sine theta over cos theta. With that, the plot of tangent theta versus theta takes the graphical form on the right. Tangent theta is also a periodic function, but it repeats in its shape every 180 degrees. Next, we're going to look at how a sine curve would change when its a, b, and c constants are changed. In the first instance, where y equals a sine x with varying a scales the y value of the curve with respect to the x-axis. In the second instance, where y equals sine bx with varying b scales the frequency of the graph cycle. And in the third instance, where y is equal to sine x plus AO, C translates the curve in the y direction. It is worth noting that when A, B, C is positioned for both cos and tangent, it behaves in exactly the same manner. For completeness, I wish to walk through a y equals modulus sine x curve. Just like any other functions, you would start by plotting the graph without its modulus, and in this case, y equals sine x, as shown above. Then, flip all negative values of y against the x-axis, as shown below, to get to the required y equals modulus sine x curve. With that, we move on to tutorial question 1, requesting us to state the equation of the graph below. From its shape, we know that some sort of an a cos bx plus c graph, where a is half of the difference between its highest and lowest y value, and this comes to 3. And b being the number of periods for the theta ranging from 0 to 2 theta, and this is 2. In this case, c is 0, as the graph does not have a translation in the y direction. Hence, the required equation is y equals 3 cos 2x. Tutorial question 2. State the equation of the graph below. From its shape, we know that it's some sort of an a sine bx plus c graph, where again a is identified from the half of the difference between its highest y value and lowest y value. This comes to 2. B is the number of periods for theta moving from 0 to 2 pi, and in this case, it is 2. Finally, C is minus 1, as the graph translates by 1 in the negative y direction. Hence, the required equation is y equals 2 sine 2x minus 1. That's all for trigonometric graphs. If you found this beneficial, do spend time on our other videos under the KT tutorial channel.